We stated earlier that in order for a limit to exist, it had to be approaching this finite number which we are using the capital L to notate. And so one of the reasons that a limit might not exist is because the function is growing unbounded in a particular area. And so one of the first functions we learn that grows unbounded, let's just take a look at the function f of x equal to 1 over x. Well, we know from the graph of this function, or even just from looking at it, that if I take 0 and substitute it in, I know that f of 0 is undefined. Because what I get is 1 divided by 0, which I can't have. And what the graph of this function looks like is for x being positive, as x grows larger, so like 1 over 2, 1 over 10, 1 over 100, the function gets closer and closer to 0. In fact, you learned in algebra that that's a horizontal asymptote. However, as x is getting really close to 0, what's happening, like if you plug 1/2 in, 1 divided by 1/2 is 2, 1 divided by 1/10 is 10. Well, as x is getting really, really small for less than 1, it's growing towards infinity, and it kind of has a vertical asymptote right there. And so my graph looks something like this. And then when x is negative, it just simply reflects it because now I'm dividing by a negative number. But the same idea happens. I end up with a graph that looks something, to the best of our ability, that looks something like that. And it doesn't have to be a perfect graph. We just need to be able to observe what's happening around the area where x is approaching 0, because that's the point where we're going to focus on when we write the limits of this function. Well, again, I can break this down one-sided. I can say the limit as x approaches 0 from below of f of x. So in other words, if I'm tracing over my function, as I start tracing towards 0 from the left, then you can see what's happening here. I'm growing larger and larger towards infinity, but just in a negative value. And so what I can actually say, you can actually say that this is negative infinity. But it's very important that you understand that because it's not a finite value, this limit still does not exist. The limit doesn't exist. We're only using this idea of negative infinity to describe the behavior of the graph. And in fact, one of the things we'll do later on is we'll make a very strong connection to this statement right here and the idea of a vertical asymptote. Now then, the limit again, going to negative infinity, but that means it doesn't exist because it's not a finite number. Now then, if I take a look at the limit as x approaches 0 from above of this particular function, meaning if I'm approaching 0 from the right, my function's growing still unbounded, but now it's growing towards positive infinity. And again, this infinity is just describing a behavior. The limit still does not exist. And we'll be able to apply that definition of one-sided limits. We're going to negative infinity from the left, positive infinity from the right. They clearly don't match. And so we can state very plainly the limit as x approaches 0 of this function f of x does not exist. Now then, let's flip it around one more type of rational function. Let's throw in the function and consider g of x equal to 1 divided by x squared. And this function has a very similar properties to it. It has its decreases and increases a little bit more dramatic, but the idea is still the same. That as x is getting small, the function has this vertical asymptote at 0. In fact, we should go ahead and state that g of 0 is undefined. The graph does have a little bit more steep shape than the function to the left here, f of x. The other key difference here is that if x is now negative, the square will actually force it positive. And so this simply reflects across the y-axis, and we get something that looks like that. And now I want to again use the one-sided limits to describe what's happening as x is approaching 0. So we'll start as x approaches 0 from below of this function. And as I come at 0 from the left, you can see my function is growing unbounded, but it is approaching infinity. And again, we should probably note for ourselves that means the limit doesn't exist. We're just using that infinity to describe the behavior. Well, the limit as x approaches 0 from above of this function g of x is also headed to infinity. As I trace this from the right, it's also growing unbounded towards positive infinity. Again, that implies that the limit does not exist, but because both of these values are headed towards infinity, we can say that the limit as x approaches 0 of g of x is infinity as a way of describing that, hey, as x gets smaller and smaller, the function heads towards infinity. Remember what our limit notation means. That's what we're saying here. And again, this does imply that the limit does not exist because it's not a finite number, but we can use infinity plus or minus to describe the behavior of certain graphs, and we can use one-sided limits as part of that as well.